Doug Waples, and today I'll be sharing with you some of my opinions and philosophy about 1D modeling, a technology that is nearly 50 years old. Nevertheless, even though 1D modeling has been an important and standard technology in petroleum exploration for about 30 years, we still have much to learn about exploiting its full potential.
Some people would ask, why aren't you calling it 1D maturity modeling? Isn't that its normal name? My response is that 1D maturity modeling, or simply maturity modeling, are fine names that capture the ultimate objective of most 1D modeling studies, namely to calculate source rock maturity. However, during today's discussion of what I call the hidden benefits, you'll see that those applications have nothing at all to do with maturity or maturity calculations. They are instead knowledge and understanding that are accrued during the model building process, rather than as a result of running the models. They are hidden benefits in that they aren't usually the stated objective of a study, and they are often missed because we aren't looking for them, don't know how to see them, and may not even be aware that such benefits exist. So today we'll drop the word maturity and focus on the geological aspects of building, understanding, and using 1D models for a wide range of purposes. Normal applications of 1D modeling focus on one or more of the aspects of maturity shown here. We can calculate the thermal history or cooking history of any rock layer and usually express the cumulative effect of this heating in terms of a calculated vitrinite reflectance, RO, value. Alternatively, or additionally, we can calculate the amount of hydrocarbon generation from any source rock using its thermal history together with appropriate kinetic parameters for the kerogen in that source rock. Finally, we sometimes calculate hydrocarbon stability, that is, cracking of oil to lighter products in either the source rocks or in suspected reservoirs. In addition, 1D modeling is commonly used as the foundation for 2D and 3D modeling, since many geological phenomena can be investigated and optimized much more conveniently in 1D than in multiple dimensions. The better the quality of the 1D models, the better the quality of the multidimensional generation migration models. I believe that the benefits from the detailed geological analysis and integration carried out during the model building process can easily be greater than the numerical answers about hydrocarbon generation, expulsion, and cracking obtained from the finished models. In this presentation, I shall therefore focus on providing illustrative examples of ways in which this type of integrated geological interpretation can be accomplished and applied. These applications can't be neatly separated into groups because they overlap and interact so strongly. However, this listing attempts to capture the main threads we will be examining today. We'll first see how optimization is not just curve fitting. It actually can test our models and give us new insights. In addition, we'll focus particularly on the subsidence history as a rich source of information about many aspects of the geological history. Unconformities are also tremendously educational, as we fit together many bits of information about the rocks that were deposited and eroded. It's not just about thicknesses. Rates, lithologies, tectonics, and sedimentation are also critical factors. Rates, thicknesses, lithologies, and depositional environments of preserved rocks are equally valuable, as they help us understand relationships among sediment supply, transport mechanisms, and accommodation space through time. Finally, we must fit our entire rock model together with a thermal model that shows changes in the thermal framework through time. It will be a fascinating journey. The process of optimizing any variable in a basin model offers learning opportunities to those with curiosity, diligence, and scientific understanding. A need to change the calculated porosity values, for example, may suggest that the current pressure model needs revisiting. Or the deficiency might indicate that lithologies had not been properly assigned to some of the rock layers, and that by changing lithologies we might develop different lithophases and sedimentation models. Or if we simply choose to change the compaction equation or constants, we are making statements about the mineralogy and other properties of the rocks. Well-considered revisions during optimization sometimes have the potential to change exploration ideas. In this example, problematic vitrinite reflectance, that is RO data, were supplemented with new VIRF data to provide a new maturity perspective that was believed to be more reliable. VIRF stands for vitrinite and inertinite reflectance and fluorescence. The final fit to the two data sets emphasized the deep VIRF and RO data and gave less credence to the shallower data. This decision affects many of the details of our geologic reconstruction. But the decision about what data to believe is complex, involving issues related to data quality, the physical processes themselves and how well we are modeling them, and our reconstructed geological history. Specifically, in this case, the shallowest measured RO values were rejected as incompatible with the well-constrained history of continuous recent sedimentation. The projected surface RO value from the shallow trend of measured RO data was simply too high to be compatible with such a scenario. Unfortunately, the reason for the high near-surface RO values was never discovered. The measured reflectance gradient from 2,200 meters to 3,300 meters looks more realistic, but it can't be fit with a reasonable thermal model because the starting RO values at 2,200 meters are too low. The parallelism between the measured and calculated trends over this depth range suggests that the geothermal gradient is appropriate, but that systematic suppression of RO values may have occurred. The very low measured reflectance gradient in the uppermost 2,200 meters of the well was also rejected, since those data could only have been fitted using unreasonable geothermal gradients and thermal conductivities today and in the recent past. Because I suspect the root cause is a systematic problem with the measured RO values, and to a lesser degree the VIRF data, I don't feel an obligation to change my geologic model to fit those data. Decisions like this one are subjective, but are often necessary when we acknowledge that all types of data and information have intrinsic uncertainties. In fact, a major problem in many optimizations is slavish obedience to data points that may in fact be very uncertain. In the end, our final calculated profile agrees only with the deepest VIRF data and some of the deepest RO values. The poor overall fit to the complete maturity data set, together with the difficulty in finding a geologically reasonable model that is consistent with the shallower RO data, suggests internal inconsistencies in the measured data that deserve further attention. More positively, the fit at the greatest depths suggests that our proposed recent burial and thermal history is yielding reasonable results in the part of the section we are likely to be most interested in. I believe that one of the greatest virtues of 1D modeling is its unique ability to help us uncover and tell the geologic story of a study area. I thus view basin modeling as a forensic science in which clues from a wide range of disciplines are compiled, combined, and interpreted. This process requires that the persons working on a project have expertise in many technical fields, including tectonics, sedimentology, biostratigraphy, petrophysics, and geochemistry. Because no one can be expert in all fields of petroleum geoscience, one must learn to access information and advice from experts who are not formally working on the project. The key step is to create a narrative that tells the story of the rocks, how and why the basin formed, how, when, and why it was modified, where its sediments came from and how they arrived, why sedimentation rates increased or decreased at different times, what the cause was for each unconformity, what events occurred during the missing time during an unconformity, why water depth and elevation changed at specific times, etc. It is this narrative that will eventually become the source for new exploration ideas and the framework on which those ideas will be developed. So let's begin with the fascinating problem of the evolution of water depth and elevation through time. This diagram comes from our NOVA software, as do all the modeling plots in this presentation. I view NOVA as the ideal platform to build models that focus on creating a plausible historical narrative. Here we see information about elevation and water depth displayed through time at a modeled location. The rectangles and dots represent different types of data, or opinions, with the width of each rectangle indicating the time span covered by the data, and the height showing the uncertainties about paleobathymetry and/or elevation. The cyan fields represent user-specified marine episodes, while orange ones designate non-marine events. A diagram like this provides a convenient way to accommodate a wide variety of types of information, to think carefully about the significance of those pieces of information, and to appreciate their uncertainties, and to begin to put the information into a coherent narrative. This slide shows the same diagram after NOVA has automatically created a paleoelevation paleobathymetry history, the green line, that takes into consideration not only the entered data, but also eustatic sea level changes and the isostatic response of the lithosphere to depositional loading. NOVA thus provides a convenient way to reconstruct a complex history from fragmentary data. That history can and should then be interrogated further by the modeler to make sure that it accurately represents the desired story. Absolute depths and elevations are important because they will affect surface temperatures, but the magnitude and direction of changes in bathymetry or elevation are often even more important, since those changes will correlate with and reflect the existence and intensity of a wide variety of geologic phenomena, including eustasy, isostasy, tectonic subsidence and uplift, accommodation space, and sediment type and supply. The term burial history is in general use, but it has at least two different meanings. The next two slides will illustrate the difference between the more specific terms burial history plots and geohistory plots. This slide shows the burial history plot for a location in the central graben of the North Sea. On a burial history plot, the datum is always the top of the solid surface, either the land surface or the sea floor. Burial history plots therefore record sediment accumulation and erosion, but show nothing about elevation or water depth, and are therefore not directly tied to subsidence or uplift. Burial history plots were essential in the pre-computer era of maturity modeling, and are still used by many workers. However, geohistory plots, shown on the next slide, contain much more information that is essential for integrating and understanding the tectonic and sedimentary histories. Here we have the geohistory plot for the same central graben location. Because the datum in a standard geohistory plot is paleo sea level, the plot depicts movements with respect to the ancient sea level, and therefore usually approximates quite well the trends of uplift and subsidence. It is thus possible to relate the changes in sediment thickness, water depth, and elevation to tectonic subsidence, the red line in this plot, and to user-specified tectonic events, which are shown here as overlays on the geohistory. Here I have annotated the same geohistory plot with two tectonic events proposed to have occurred during the early history of the basin. We see Jurassic rifting that resulted in a rapid and substantial increase in water depth, followed by a very slow partial filling of the basin during the Cretaceous. The slowness with which the basin filled with sediment suggests partial starvation, and thus gives us information about the regional topography and drainage. We also note another episode of rapidly increasing water depth during the early Tertiary, and that the new deepwater Tertiary basin accumulated sediment very slowly. That is, it suffered an additional episode of starvation until the late Neogene, when it filled very suddenly. These noteworthy changes can be easily identified by carefully interrogating the geohistory plot and can then be included in the narrative. Later we shall re-examine this example in more detail as we elaborate on the story we are just starting to tell. As an aside, you may not fully agree in detail with all the interpretations offered in this presentation. Disagreement can often lead to fruitful discussion and improvements in our understanding. However, the point of this presentation is to give you ideas about all the things that you can accomplish using 1D modeling, rather than to teach you everything geological about these areas. Please don't miss our most important message while you're critiquing the interpretations presented here. Here we see the geohistory plot for a location in the Delaware Basin of West Texas, part of the Permian Basin, near the western edge of the Great Plains in the U.S. The location of the basin is shown on the next slide. Note the red tectonic subsidence line, the overlays representing numerous tectonic events that created and modified the basin, the uplift that permanently raised the area above sea level at the end of the Cretaceous, and the subsequent stepwise tertiary uplift to its present high elevation. Note also that the red-orange colors immediately identify the bulk of the sedimentary package as Permian. The Permian Basin, designated here as PB, is located on the western margin of the Great Plains, just at the leading edge of both the Laramide thrusts and the southeasternmost extension of the Basin and Range extensional volcanic province. This map also shows the locations of three other areas that will be discussed later in this presentation: the Anadarko Basin, AB, the Powder River Basin, PRB, and the Colorado Plateau, CP. Those four areas share some common characteristics, including parts of the stratigraphic section and some of the tectonic events, but they also differ from each other in important ways. In executing a study in one area, one's personal experience in other areas, and the use of analogies from one's experience base are highly commendable. However, one must always remember that no analog is perfect, and that seemingly minor differences may be critical in determining whether or not an analogy truly works. Later in this discussion, we will visit each of these areas and discuss some of the geological similarities among them. The Permian Basin, which formed as the successor to the ancient passive margin Tobosa Basin, is a foreland basin or group of basins that developed in front of the advancing suture between North America and South America during the late part of the Ouachita orogeny in the late Carboniferous and Permian. Its approximate position shortly before the suture is shown by the red dot on this map. Also shown are the positions of the two continents before the true collision, when outlying island arcs and other terrains from the two continental masses had already begun to interact. I believe that the earliest interaction resulted in up-down wrench fault tectonics that dominated from the late Devonian to the late Carboniferous, prior to the suture proper. If you wish, you can return to the geohistory plot and the tectonic overlays for the Delaware Basin to examine the consequences of these various events. This slide shows the location of the Permian Basin as the marine foreland basin that developed on the North American side of the Ouachita Suture during the early Permian. Paleogeographic maps, like Professor Blakey's, are very useful in helping us develop conceptual links among tectonics, basin evolution, and sedimentation patterns, which include facies, lithologies, sources, transport, and thicknesses. This slide shows a geohistory plot in the Midland Basin, which is the eastern part of the Permian Basin. The sediments, which are dominantly of Permian age, as shown by their red-orange colors, were deposited toward the end of the Ouachita orogeny, a long enduring process that began earlier to the northeast, into Oklahoma and even earlier in Arkansas and Alabama. Find the similarities and differences between this geohistory plot and the one for the Anadarko Basin shown in the next slide. Our earlier map showed that the Anadarko Basin is located just to the north-northeast of the Midland Basin. This geohistory plot is for a location in the Anadarko Basin of Oklahoma, which sits just to the north-northeast of the Permian Basin. The Anadarko Basin was also formed as a foreland basin in front of the Ouachita Thrust, but it formed earlier than the Permian Basin, as shown by the dominance in the Anadarko of greenish Mississippian and gray Pennsylvanian Carboniferous rocks, rather than orange Permian strata. This comparison illustrates the value of finding and utilizing appropriate analogs. Those who understand the Permian Basin will be able to adapt that understanding to the Anadarko Basin and vice versa. Moreover, ideas relevant to the Permian Basin that have never been applied in the Anadarko might be tested to see if the analogy leads to new insights or exploration ideas. The main caution in using analogies, of course, is that no analog is a perfect twin. In fact, when working with analogies, it can be more instructive to focus on the differences than on the similarities. Ideally, interpretation of geohistory plots should include the effects of eustatic sea level changes. This slide shows NOVA's default global sea level curve for the Phanerozoic. Variations in sea level through time can be shown on geohistory plots, as displayed in this plot at a location in the North Sea. This format utilizes present-day sea level as the datum, and thus allows sea level to go up and down through time. The variations in sea level, in turn, influence the calculated position of the sea floor, which influences the tectonic subsidence curve. This format is not common today, but may become more popular in the future, as sea level considerations are integrated more thoroughly into basin modeling. Most geohistory plots today use paleo sea level as the datum, and thus show the ocean surface through time as a flat surface. Extensional processes are important in the formation and modification of many sedimentary basins. The terms rift and rifting are often used interchangeably with extension. However, not all features that are termed rifts are identical or ideal. Equatorial Guinea, represented by the black dot on this slide, is located on the rifted southern part of the West African margin, and thus might be naively assumed to represent an ideal rift-drift scenario. However, on closer examination, we note two potentially important complexities in this area. Equatorial Guinea is located very close to the eastern end of the east-west trending transform fault zone along the bulge of West Africa. And there is a northeast to southwest trend of structures, the Cameroon volcanic line, just to the west of the black dot on this map. These potential complications to our conceptual model of simple rifting and drifting will be discussed in the following slides. A geohistory plot for a location in Equatorial Guinea shows the expected rapid initial subsidence during rifting of the South Atlantic, followed by very slow subsidence during drifting. However, the plot also shows a number of subsequent unconformities and irregularities in the subsidence history that would not be expected in a simple rift-drift scenario. In particular, the uplift that is proposed to have begun in the Eocene at about 40 million years may well have been associated with the early development of the Cameroon volcanic line, whose oldest volcanism is dated at about 30 million years. Two other unconformities, the smaller pink arrows, are also anomalous. This slide shows in map view that the Cameroon volcanic line is itself only a small part of a larger story. The CVL lies along the southwestward extension of the Central African Shear Zone, CASZ, which links the central Atlantic coast of Africa to both the Red Sea and the East African Rift System. We see that, far from being a quiet spot on a passive margin, Equatorial Guinea actually sits in a very tectonically complex position. This complexity is in turn reflected in the irregularities in its tectonic subsidence history. And armed with a better understanding of the true tectonic setting, we should now also anticipate possible abnormalities in its thermal history. Unfortunately, we won't have time here to discuss that important part of the story. But we can easily go a bit further in our analysis of the rifts of Africa. The Muglad Basin of Sudan, which sits at the junction of the CASZ and the East African Rift, is also often referred to as a rift. However, the geometry of the rifting across Africa would make it nearly impossible to maintain true simple rifting for very long at any location. Eventually, compression would occur, at least locally, and much of the subsequent movement might be better described as wrench or pull-apart tectonics. A geohistory plot from the Muglad Basin shows numerous unconformities that suggest to me that it might be better considered as a wrench or pull-apart basin, in which periods of extension alternated with periods of compression, uplift, and erosion. The most important takeaway from these examples is that not all basins labeled as rifts are alike, and some would probably be better given other designations. Be cautious about the use of analogies in so-called rift settings, and consider the broader plate tectonic scenario as well as local seismic and stratigraphic data. The Gulf of Mexico is understood to be a failed rift that was nevertheless successful enough for oceanic crust to have been created in the central part. This slide shows a map that includes the Gulf of Mexico. Here we will discuss an offshore example shown from the southern Mexican part, the Gulf of Campeche, as indicated by the hatchered circle. Please also note for future reference the position of the Chiapas fold and thrust belt in onshore southern Mexico. A geohistory plot from the Gulf of Campeche shows a typical rift-drift scenario that lasted from the Middle Jurassic until the end of the Cretaceous. Salt was deposited during the earliest marine phase. Water depth increased rapidly during rifting and remained deep for a long time afterward during the drift phase. Taken together, the lack of clastics in the highly calcareous post-salt sediments, the low sedimentation rates, and the maintenance of deep water conditions provide excellent evidence for long-lasting sediment starvation until the end of the Cretaceous. This paleogeographic map shows the modeled location in the Gulf of Campeche, the red dot, at the start of local rifting in the Middle Jurassic. The Triassic Rift, centered near the yellow dot in the northern part of the Gulf of Mexico, was already well developed by this time. This paleogeographic map at 105 million years, during the Albian, shows that rifting in the Gulf of Campeche has joined the main rift, but that the degree of extension in the south is much lower than in the northern Gulf. The depositional environment has now become fairly open marine, but because there is no major source of clastics, the sediments continue to be dominated by carbonates. This series of maps shows the value of integrating paleoenvironmental and paleogeographic information into the interpretation of geohistory plots. The typical drift sequence was terminated near the KT boundary by a simultaneous but modest increase in the rates of both tectonic subsidence, shown by the red line, and sedimentation, shown by the steepening of the geohistory curves. These initial changes were followed in the Cenozoic by two further increases in the rates of both tectonic subsidence and sedimentation. The first of these increases occurred in the late Oligocene, and the second at the end of the Miocene. A good basin modeler soon learns to be skeptical of coincidences, which actually often represent either a cause and effect relationship between coincident phenomena or a common cause for those phenomena. We should therefore ask whether the three increases in tectonic subsidence rate might have related causes, and whether the three increases in sedimentation rate might also be somehow related to each other. Furthermore, we should ask whether the increases in sedimentation rate are somehow related to the increases in tectonic subsidence. We'll examine some possible explanations for these phenomena and those so-called coincidences in the next slides. To understand what happened in the Gulf of Campeche from the late Cretaceous to present day, we must look at the plate tectonic history of the Pacific Ocean and the western margin of North America. Stepping back to a plate tectonic scale is usually a wise decision prior to plunging into any deep and detailed interpretation of local tectonic events and their consequences. This slide depicts the subduction of the Farallon Plate beneath western North America during the Mesozoic. The location of the study area is approximately indicated by the red dot, which, despite its current location in the Gulf of Mexico, was at that time not far from the Pacific coast of Mexico. This Eocene paleogeographic map at 50 million years shows the study area as a red dot. The red arrow indicates the material being accreted onto the west coast of Mexico from the downgoing Farallon Plate. This accretion, which may represent the earliest phase of development of an ancestral Chiapas thrust and fold belt, could have resulted in Foreland Basin type loading subsidence to the north in the study area. The simultaneous increase in sedimentation rate in the Gulf of Campeche, which we noted earlier on the geohistory plot, would thus have been the result of development of a larger hinterland with greater topographic relief and mass. At the end of the Cretaceous, indicated by the green arrow, the rates of both tectonic subsidence and solid sediment accumulation slowly began to increase, and the rates accelerated continuously until near the end of the Miocene. We may be able to account for the acceleration in tectonic subsidence as the result of loading to the southwest by an ancestral Chiapas thrust and fold belt, and the resulting new emergent landmass would have increased the supply of clastics. We therefore can link tectonic subsidence to plate tectonics in two ways: subduction of the Farallon Plate and accretion of exotic terrains to the southwest. And we can link the plate tectonics events to the increase in sedimentation rate. It makes a very neat story. But there are still a few problems with our reconstruction. First, the sedimentation rates from the Paleocene to almost the end of the Miocene were not high. The new hinterland was thus only a modest source of sediment that could barely keep pace with the loading-induced tectonic subsidence. In this slide, we see that water depth hardly decreased until the end of the Miocene. We therefore should view the early version of the Chiapas thrust and fold belt as a very modest feature that neither caused extensive Foreland Basin-style downwarping to the north, nor provided much sediment. The second issue with our reconstruction is that the tertiary sediments in the Gulf of Campeche, shown in yellow and orange colors in this table, are more calcareous than the green Mesozoic sediments. One would intuitively expect that an increase in the proportion of clastics would decrease the carbonate content. However, this issue is actually an illusion, since the eroding Chiapas highlands are limestones rather than crystalline basement or clastic sediments. The table shows that the late Pliocene to Pleistocene section is the most calcareous and has the highest sedimentation rates. These observations suggest that the contribution of sediments from the Chiapas fold and thrust belt is at its historical maximum today. In fact, the recent sedimentation rates were so high that the basin finally became full after 150 million years of starvation. This filling occurred in spite of an increase in the rate of tectonic subsidence in the last 5 million years, as indicated by the arrow. The increase in both tectonic subsidence and sediment supply during the last few million years indicates either that the tectonic history has changed radically in character or that those events have simply strengthened. I believe in the latter explanation, that orogenic activity in the vicinity of the Chiapas thrust and fold belt has increased significantly, and think that the plate tectonics provides a good explanation. This plate map shows present-day subduction relative to the positions of the Gulf of Campeche, the yellow dot, and the Chiapas thrust and fold belt, indicated by the dark red oval. The downgoing Cocos plate, shown in pink, is an active daughter of the defunct Farallon plate. It has been involved in much of the tectonic activity that created the strong recent tectonic subsidence and produced the large volumes of sediment that have recently filled the basin. For example, a paleogeographic map at 20 million years depicts the ongoing accretion of material carried by the Cocos plate. This accretion increases both the amount of loading in the Chiapas thrust and fold belt and the rate of tectonic subsidence in the new Foreland Basin in the study area. This series of slides and this example emphasize the value of combining data and displays from a variety of sources and disciplines as an aid in learning, developing new ideas, and communicating those ideas in conclusions. This is an unannotated geohistory plot for a typical location in the central graben of the North Sea, with tectonic subsidence superimposed in red. Our first objective in analyzing this plot is to identify significant events and changes. One of the first things we might note is a non-marine phase during deposition of the oldest layers modeled, followed by marine deposition that has lasted to present day. We also see that, as in the Gulf of Campeche, water depth increased rapidly in the Jurassic during rapid and major tectonic subsidence, and that this phase was followed by a long period of tectonic quiescence in which the basin failed to fill with sediments. We also see a second period of rapid tectonic subsidence in the early Tertiary, where again the basin failed to fill. Finally, we see a rapid tectonic uplift that occurred synchronously with the final filling of the basin. These basic observations can help provide a framework on which we can reconstruct the geologic history. Similar observations can be made for any geohistory plot. I have begun the detailed analysis by focusing on a single tectonic event, the failed rifting that created the central graben during the Jurassic, and by superimposing that event on the geohistory plot. For many observers, this event is the defining one in the basin's history. However, I prefer to consider it as simply a convenient starting point for putting together a more comprehensive story. In particular, my eyes are drawn to the rather long history, extending back to deposition of the Permian Zechstein Formation, the oldest event considered in our models. Deposition of the Zechstein predates the failed Central Graben Rift. The pre-rift events remind us that the basin did indeed have a history prior to the formation of the Central Graben, and that understanding that early history may be important for fully understanding the Central Graben Rift itself, as well as the basin's thermal history. Here I have therefore superimposed an earlier tectonic event that represents the formation of the older and larger Northwest European Basin. For the purposes of this discussion, I have not carried out a full analysis of the history of the Northwest European Basin, but I have included the late events in its history as part of the context for understanding the formation and evolution of the Central Graben. I have labeled the Northwest European Basin a sag basin, a term that suggests some parallelism with early Paleozoic basins in North America that have been studied in considerable detail. For example, the Illinois, Williston, Anadarko, and Michigan basins. As noted earlier, because cautious use of such analogies can be valuable, suitable analogs should always be sought, and experts on those analogs should be consulted. We note that both our sag and rift phases show considerable tectonic subsidence. In fact, the amount of sag subsidence since the Zechstein is about equal to the rift subsidence, and if we included the earlier part of the sag phase, the total amount of sagging would surely have been greater. However, the Jurassic rift subsidence occurred quickly, within 20 to 25 million years, whereas the sag subsidence during deposition of just the Zechstein and Triassic layers lasted for about 60 million years. The slowness of the tectonic subsidence during the Paleozoic and Triassic is a major reason that I called the Northwest European Basin phase a sag rather than a rift. The Jurassic rifting led to major rapid tectonic subsidence and quick development of bathyal marine conditions, which then persisted for the first 20 million years of the drift phase. The basin finally began filling at a moderate rate during the Cretaceous. During and after the drift phase, there were a number of unconformities, whose occurrence either contradicts our proposed deepwater history or requires non-deposition and possibly even erosion under deepwater conditions. This issue clearly requires additional attention in our analysis, as it poses serious questions that will affect our overall understanding of the basin. If our water depth reconstructions are correct, basin filling seems to have begun during the Aptian, as shown by the black arrow. This change implies the appearance in the Aptian of a new source of sediment. It would be logical and perhaps very useful to know whether the influx of sediment was related to a tectonic event that created a new erodible feature, or simply tapped into a pre-existing sediment source that was not previously able to reach the Central Graben. Filling of the basin continued at a modest rate until the Paleocene, when the water depth increased abruptly from outer shelf to middle bathyal, as shown by the blue arrow. Such a rapid and large change must surely have been tectonic in nature, and indeed, the tectonic subsidence curve moved strongly downward. That subsidence was very possibly due to wrench faulting, similar to that in the onshore and offshore basins of Southern California during the Neogene. Because such major tectonic activity could also have led to deposition of reservoir or source rocks and the formation of structures, this tectonism should be carefully reconstructed and studied. The Paleocene tectonic activity heralded an exponential increase in sedimentation rate, as shown by the increasing slope of the burial curves for the Eocene and younger rocks on previous slides, and by the calculated solid sedimentation rates shown in this slide. However, the increased sediment supply was still not great enough to immediately fill the basin. The probable cause for the sediment deficiency might have been a lack of uplift in the surrounding region, or the inability of sediments derived from uplifts to make their way immediately to the modeled location. Sedimentation rates during the Plio-Pleistocene, however, have finally been high enough to begin to fill the basin. The present-day shallow water depths are the result of the combined effects of very rapid recent sedimentation. But why only so recently, and where did the sediment come from? And some tectonic event, as indicated by the upward trend of the red tectonic subsidence line during the past few million years. In our Gulf of Campeche example, lithologies played only a minor role in our overall interpretation of the geohistory plots. In the North Sea, in contrast, they play a key role in understanding the history around the KT boundary. The sediments deposited at the end of the Cretaceous and the early Paleocene were all nearly pure chalks, which are highlighted in red in this slide, and sedimentation rates were moderate. These facts indicate good productivity of phytoplankton, particularly coccolithophorids, probably in an outer shelf environment, where upwelling of nutrients was occurring. The absence of a significant source of clastics allowed deposition of a substantial thickness of pure chalk. The rapid and sudden increase in water depth in the mid-Paleocene seems to have terminated chalk deposition, probably by transferring the upwelling zone elsewhere. However, the continuing absence of a major source for clastics resulted in an immediate 80 to 90% decrease in the sedimentation rate, which is clearly visible in this table in going from the Ekofisk chalk, shown in red and deposited at about 50 meters per million years, to the shales of the Lista, Selly, and Boulder formations, highlighted in yellow, which were deposited at about 10 meters per million years. This post-chalk period of slow deposition ended abruptly with an influx of clastics in the Horda Formation and subsequent units. Not being an ardent fan of coincidence, I suggest that the clastics in the Horda and younger units came from mid-Paleocene uplifts that occurred during wrenching events that ended chalk deposition forever. Areas dominated by strike-slip faulting are likely to have alternating highs and lows, called porpoise structures, representing local variations in transpression and transtension through time and space. I suspect that sediments derived from such highs were not available to the modeled area during slow deposition of the Lista, Selly, and Boulder units, possibly because they were being channeled into an intervening basin. Obviously, more geological and geophysical work is needed to test these ideas. Reconstructing unconformities in detail is a fascinating and highly valuable process. Unfortunately, this task seems to have little appeal for many basin modelers, and is therefore seldom given the attention that it merits. I personally find it to be one of the keys to increasing one's understanding of geological history and to generating new exploration ideas. Better reconstructions of unconformities obviously will also improve our calculations of maturity, expulsion, and migration, and thus also increase confidence in our results. The example here is from the Midland Basin, which, as we have seen, is part of the Permian Basin system of West Texas. Cretaceous sediments are completely missing in part of the basin and are mostly absent over the rest. The total Cretaceous that is believed to have been deposited and later removed is thick enough to have significantly affected maturity at many locations. In addition, a detailed reconstruction of the depositional and erosional history of the area will tell us much about the tectonic environment during both the Cretaceous, when deposition was occurring, and the Cenozoic, when the erosion of those deposits took place. This reconstruction will also require integration with our conceptual model for the development and evolution of the Western Interior Seaway, including depositional conditions and facies. In our reconstructions, we divided the Cretaceous, which here is Albian to Maastrichtian, into 9 sedimentary packages, separated by 5 brief unconformities that we assume to have been hiatuses. These 14 events, plus another one representing deposition of hypothesized non-marine Paleocene sediments, are represented at one location here by the downward irregular trajectory on the left side of the depth diagram. The original thickness of each unit at each model location was estimated using a facies approach that was constrained by preserved rocks in several measured sections surrounding the Permian Basin. We then eroded all of the missing rocks in 2 stages, following simple rules that we created to fit our tectonic concepts. First, erosion from 60 million years to 5 million years was constrained to be relatively slow, since the sole driving force was the laramide uplift, which was weak on the western Great Plains. Second, in contrast, erosion from 5 million years to present day, driven by the rapid uplift and eastward tilting of the Great Plains, was much faster. Third, lacking detailed knowledge, we kept the rate of erosion constant within each of those 2 phases. The result is the 2-step upward trending erosion profile shown on the right side of the diagram. If we had wished, we could have adjusted erosion rates further to reflect lithologic variations. This approach is significantly different from, and more reliable and informative than, a more traditional approach to reconstructing unconformities, where the entire Cretaceous section might be lumped together and a single total thickness of missing Cretaceous estimated. Even if the final total proposed eroded thicknesses are similar, the detailed reconstruction allows us to consider the evolution of the Cretaceous facies through time, and thus to understand the influence of both tectonics and eustatic sea level changes on Cretaceous deposition. One takeaway for us from this experience was the clear recognition that the Western Interior Seaway had to have a substantial component of tectonic subsidence as a foreland in front of the advancing laramide orogenic sheets. Because without this tectonic subsidence, the seaway could not have accumulated the thicknesses of sediments known to have been deposited there. The Colorado Plateau, outlined here in black, covers a wide area in the western U.S. It takes its name from the Colorado River, which flows through it from northeast to southwest, where it is incised the Grand Canyon. The Colorado Plateau has been strongly affected by a number of tectonic events, as shown and discussed on the following slides, which include geohistory plots for the wells shown by the red dot. This slide shows the location of the Colorado Plateau, CP, in comparison to the Anadarko Basin, AB, and Permian Basins, PB, discussed earlier, and the Powder River Basin, PRB, to be discussed later. Lying furthest to the west, the Colorado Plateau was affected earliest by tectonic events related to subduction along the ancient western margin of North America. The geohistory model shows that the pre-severe history was very mild, and that the severe orogeny began with accretion of microcontinents onto western North America during the late Triassic. Continuing compression during the Jurassic resulted in loading-induced tectonic subsidence that produced a minor foreland basin at this location. Laramide thrusting to the west resulted in downwarping and formation of another foreland basin in the early late Cretaceous. At this location, and across most of the western U.S., the Laramide effects were much greater than those of the severe orogeny. Here I will emphasize the several uplift events that occurred during the Tertiary: Laramide, Basin and Range, and Great Plains, as shown superimposed on this geohistory model. The earliest, the Laramide, represented inversion of the late Cretaceous to Paleocene Laramide foreland downwarp, as subduction of the Farallon Plate advanced eastward. The subsequent Basin and Range thermal and tectonic event was of highly variable magnitude across a vast area. Here I have assumed that considerable Basin and Range uplift occurred during the Miocene. Finally, the Great Plains uplift during the past 5 million years has resulted in major uplift with down to the east tilting. Next, we will discuss in detail our reconstruction of surface elevation through time using a wide variety of data types and sources. In doing so, we will carefully consider erosional events and rates as well as uplift. This slide zooms in on the geohistory plot from mid-Cretaceous to present day. Among the major questions about this history are the amount and timing of Laramide uplift and the effect of that uplift on surface elevation during the Paleogene. The elevation at which the famous lacustrine Green River Shale, GRS, was deposited is a key to understanding the timing of the Laramide uplift. The common presence of crocodile fossils in the Green River is important because modern crocodiles, which surely were biologically very similar to Eocene crocodiles, do not live where mean annual surface temperatures are less than 23 degrees Celsius. By combining our knowledge of paleolatitude, global climate through time, and an estimate of the decrease in surface temperature with elevation gain, we could establish a maximum surface elevation during Green River time. That calculation was key in concluding that the Green River Formation was deposited close to sea level, and that all or most of the Laramide uplift therefore postdates the lacustrine sequence. In fact, since I don't believe much in coincidences, I think the Laramide uplift was probably responsible for destroying the stable conditions that enabled deposition of lacustrine facies for several million years during the Eocene over large areas of the western U.S. This slide zooms further into the Neogene history of this model, in which we can examine details not visible on a coarser scale. For example, we note emplacement of a substantial extrusive basalt layer, shown in yellow, at about 10 million years, in the Tortonian stage of the late Miocene, during the Basin and Range uplift event. In our model, erosion began immediately after extrusion, but was very slow until 5 million years, when the basalt layer suddenly disappeared. So the question arises, why did the basalt erode so suddenly and yet erratically, since this basalt still caps the mesas in western Colorado? The answer is straightforward but many-faceted. First, at 5 million years, downcutting by the Colorado River began as the main drainage in the western Rocky Mountain region switched from eastward toward the Mississippi River and the Gulf of Mexico to westward toward the Gulf of California. Second, the land rose due to the Great Plains uplift and possibly as a continuation of the Basin and Range uplift, creating a high topographic gradient for western flow. And third, the barrier to flow all the way to the Gulf of California was removed when the dam that led to formation of the ancient huge lake in southern Utah was breached. The cutting of the Grand Canyon within just the past 5 million years is testimony to the erosional power of this system once it was unleashed. In our model, erosion rates have varied through time, particularly during the past 6 million years. We varied erosion rates based on two principles: variations in the driving force caused by changes in water volume and/or hydraulic gradient, that is, elevation divided by distance, and variations in the resistance of the different layers being eroded. The slowest erosion in our model occurred before 5 million years, when the hydraulic gradient was low and basalt, the most resistant layer, covered much of the regional surface. From 5 million years onward, the erosion rate of the basalt increased as the Colorado River began its incision into the plateau. After the basalt disappeared, by about 3.5 million years at this location, the softer non-marine deposits were eroded quickly until the cemented Green River carbonate was reached at about 1.5 million years, causing the erosion rate to drop. Slow Green River erosion was followed by rapid erosion of the uppermost marine Cretaceous units, with a major increase in erosion rate at about 0.2 million years. The intensity of recent erosion is suggested by movement of huge boulders for distances up to tens of kilometers. Until 5 million years ago, the surface elevation in our model was rising as uplift rates exceeded erosion rates. From 5 million years to present day, in contrast, we believe that the surface stopped rising and even lowered slightly in the last 1.5 million years in response to increased erosion rates. The decrease in surface elevation occurred in spite of an increase in the rate of tectonic uplift, which is shown by the red line. Present-day elevation is therefore not the maximum. The surface stayed at about 1,800 meters above sea level between 4 million years and 1.5 million years ago. Does this detailed reconstruction of the unconformities affect maturity calculations? Probably not in this case, nor in many other cases. But a careful reconstruction of unconformities pays dividends in leading to a deeper understanding of the forces and interactions that control uplift, subsidence, sedimentation, lithologies, and amounts of erosion. This improved understanding, as I have already said, will eventually turn out to be valuable in generating new geological concepts and exploration ideas. Although we won't spend much time on thermal issues in this presentation, we will have a quick look at some aspects of paleosurface temperatures, convective heat transfer, and basal and surface heat flow. Paleosurface temperatures depend on the 4 factors shown in this slide. Although many modelers use a constant surface temperature through time, I prefer to create complex temperature histories for 2 reasons. First, and most obviously, surface temperature can vary considerably, particularly over long periods of time or when there are extremes of water depth or elevation. Many models will show variations of at least 15 degrees Celsius, and variations of 20 to 25 degrees Celsius are common. In extreme cases involving snowball Earth or icebox Earth models in the Precambrian, variations will be much larger. Second, by thinking carefully about the factors that control surface temperature, one is induced to build a more intelligent and better integrated model for the tectonic, burial, and erosional history. Making a strong effort in the area of paleosurface temperatures is thus a valuable step in building good geologic models. Fortunately, NOVA makes the process of creating a surface temperature history very easy. The purple line in this slide represents the reconstructed paleolatitude for a model location in the Delaware Basin, part of the Permian Basin. Paleolatitude influences paleosurface temperature, but it also gives us information about plate and regional tectonics. Over the past 450 million years, latitude in this model has ranged from 40 degrees south to 40 degrees north, including considerable time spent near the equator. For reference, and as an additional opportunity to integrate different parts of the geologic model into a conceptual whole, I have annotated the plot with various events in the history of the Delaware Basin. In this case, the northward movement of North America was stalled near the equator during the existence of Pangaea, and only resumed moving when North America broke away again in the Triassic. Is this a discovery of importance? Has it ever been discussed by others? Might it give insight into the mechanism and causes of the disintegration of Pangaea? The line in this slide represents the calculated surface rock temperature through time for the same model location in the Delaware Basin. As noted earlier, paleo surface temperature was calculated from information about latitude, global climate, elevation, and water depth. Paleo surface temperatures range from about 15 degrees Celsius to 33 degrees Celsius, values that are in general quite different from the standard value of 15 degrees Celsius recommended by some modelers. Errors in paleo surface temperature will of course propagate errors in calculated subsurface temperatures and should therefore be avoided. This slide shows a comparison of trends in calculated paleo surface temperature, blue, and global climate, red. The overall similarity of the trends indicates that paleo surface temperature in this model was mainly controlled by global climate. A few disagreements, however, indicate that other factors occasionally became dominant. For example, in the late Carboniferous, the black arrow, the trend of surface temperature diverged significantly from that for global climate. This discrepancy is discussed further on the next slide. This plot compares trends in paleo surface temperature, shown in blue, and water depth and elevation in orange. The Carboniferous surface temperature anomaly mentioned earlier is now revealed as a time when water depth briefly decreased by a large amount. Conversely, the recent drop in surface temperature correlates with a major uplift of the land surface above sea level. Discussions of surface temperature often lead to discussions of subsurface temperatures, which in turn lead to questions about heat flow. Maps of surface heat flow, when based on abundant and high-quality data, can be very helpful. This standard map of the surface heat flow in the U.S. is highly valuable, not only in understanding trends, but also in recognizing the possible underlying causes for unusual values. The major limitations to this map are the uneven and sometimes inadequate data density, and concerns about how the mapped heat flows were determined. As we will see later, a generalized map like this one can easily miss local anomalies and may create anomalies that are actually a result of poor data quality. Surface heat flow, which is usually what is shown in maps like the one on the previous slide, is different from basal heat flow, which is the value we enter into basin models. Radiogenic heat produced by the radioactive decay of uranium, thorium, and potassium in each sedimentary layer is added to the basal heat flowing into the simulated section from below. What we call basal heat flow is often, but not always, the heat flow at the top of basement. The amount of sedimentary radiogenic heat varies greatly with lithology and mineralogy, and high porosities decrease radiogenic heat production because pore fluids are essentially non-radiogenic. In this example, the greatest radiogenic heat production is in the middle part of the section because those strata are richest in clay minerals. The deepest rocks tend to be more calcareous, while the shallowest ones are either evaporitic or calcareous. We could see a few exceptions to this trend. For example, the organic-rich Woodford Shale is highly radiogenic. The brown profile shows the vertical variation in heat flow, with values increasing upward due to addition of radiogenic heat. The amount of heat added by each rock layer depends on its thickness and its radiogenic heat productivity. The slope of any segment of the heat flow profile thus depends inversely on the total thermal conductivity of that rock layer. This plot shows how important it is not to confuse basal and surface heat flow. It also shows that there is no single heat flow value that summarizes the entire heat flow story. In understanding and telling the heat flow and thermal profile stories, one must separately consider each of the components, including heat capacity effects during active sedimentation and erosion that are not evident in this example. This slide shows a portion of the map of the U.S. surface heat flow, with the outline of the Powder River Basin in northeastern Wyoming to southeastern Montana shown as a black oval. The published map of surface heat flow shows a rather uniform surface heat flow across the basin, with a few areas of slightly anomalously low values. Total variation in surface heat flow across the basin is less than 10 milliwatts per square meter. The amount of data in the Powder River area and the sources and quality of those data are not specified on the map. In our study of the Powder River Basin, we created an independent map of surface heat flow. The total range of values on our map is about 30 milliwatts per square meter. That is, we see 3 times as much variation in surface heat flow as is shown on the published map. Moreover, our lowest values, in purple, all hug the western margin of the basin, and values increase eastward, with our highest values, in red, along the southeastern margin of the basin. Our surface heat flows were simply those derived from the basal heat flows required to fit the downhole temperature data, using what we considered to be reasonable values for surface temperature, thermal conductivity, porosity, heat capacity, and radiogenic heat production. We believe the surface heat flow values across much of the basin have been strongly affected by groundwater flow, rather than purely by conductive heat transfer, as is normally assumed in basin modeling. We interpret the low values to the west, in and adjacent to the Bighorn Mountains, as indicative of recharge by cold water from melted snow and rain at high elevations. Those effects diminish eastward as the groundwater warms. In contrast, we interpret the high surface heat flows along the eastern margin as representative of discharge zones, where hot water is emerging from the deep basin. Our work in the Powder River Basin has thus updated and considerably improved our understanding of both hydrodynamics and geothermics in the basin. A logical subsequent step would be to try to model the evolution of the groundwater model so that we know its effect at different times in the past. Another step would be to apply this approach to other basins that might have been affected in similar ways. Although this has been a long seminar, we haven't had time to cover all possible interesting topics that could be valuable and relevant in understanding the integrated geologic history of an area. Among the subjects we haven't considered at all, or only superficially, are other aspects of convective heat flow, including igneous intrusions and hydrothermal activity. We also haven't discussed the question of varying heat flow through time and its relationship to different types of tectonic events, such as rifting, pull-aparts, and foreland basins. There's been no significant mention of the lithosphere, types of crust, the lateral and vertical variability of the various layers of the lithosphere, and their properties, and changes in the lithosphere through time. We've only touched briefly on the properties of the sediments that fill basins. That topic would include not only lithology, mineralogy, provenance, and porosity, but also issues directly related to temperature, such as heat capacities, thermal conductivities, and radiogenic heat production from both sedimentary rocks and from the lithosphere. Finally, we haven't directly mentioned putting our modeled stratigraphy into a sequence stratigraphic or chronostratigraphic framework. These are all fascinating and valuable areas that one can and should consider in building the best possible models. In an effort to summarize what I think are the most important takeaways from this discussion, I'd like to reiterate that 1D modeling is a unique, powerful, and extremely valuable tool for investigation and integration of ideas and data from the various disciplines within geology, and for application of those ideas in petroleum exploration. Unfortunately, this approach has not yet been widely adopted, and therefore has not impacted exploration work as much as it should have. I hope each of you can find a way to make a contribution in this area. It is the geologists, rather than the geochemists and professional basin modelers, who are best equipped to perform this type of integration and analysis. My emphasis on the crucial role of normal exploration geologists comes from my conviction that geologists know their exploration area better than outsiders do, and thus can have important insights that a modeling expert would never think of. Becoming a successful basin modeler requires curiosity, open-mindedness, creativity, the ability to work with open-ended, incomplete, and often contradictory or confusing data sets of many types, and a desire and ability to tell stories. Good basin modeling requires support from management. Adequate amounts of time and money are essential, but those investments are easily justified for areas where a company has a significant commitment. Moral support from management is also important, since it will promote an inquiry-based approach to the subject. That said, these projects must not be open-ended or interminable, and must be responsible in their adherence to budgets and schedules. In an exploration environment, this work is not academic because it will be directly applied in making time-sensitive exploration decisions. We can never know everything about a basin, but we can keep trying to learn until the final whistle blows. And then we must tell our supporters what we have learned and how it will help them be successful.
So, thank you for your attention, and I hope very much you'll enjoy your modeling.